So yeah, my name is Daniel Kirste. I am a research scientist and postdoctoral researcher at the Technical University of Munich at the campus Heilbronn. At the campus Heilbronn, it's a pretty new campus, like 2 or 3 years old, and there we are like massively researching on AI, and that's why I also want to take you on a journey today at the intersection of my home turf, Cryptoeconomic Systems, and how they have the symbiosis with machine learning resource provisioning. Yeah, that's what I want to take you on a journey. So, to give you a better understanding, I will give you a brief overview over the machine learning resource provisioning pipeline. Why isn't this working? Okay, then I will click here. So I want to give you a short overview over the machine learning workflow. So it basically consists of three steps. First, it always starts with the preparation phase where data is acquired. So for example, if I have my Apple Watch, the first step could be simply reading my heartbeats out of my Apple Watch. Then we have data cleaning where, for example, mismeasured heartbeats are removed. And in the next step, for example, we have a data labeling where my heartbeats are labeled, where I could maybe have some arithmetics in my heartbeat, or where I have a normal heartbeat, or when I'm sleeping. In the next step, in the data preparation, we need to get the most out of this data and have a feature engineering and selection, where we basically can then choose, hey, you only want to monitor my heart data when I'm sleeping. This feature engineered data will then be used for the next step in the development phase. So in the development phase, we have an ML model selection and hyperparameter optimization. So here basically the architecture for the machine learning model gets selected and the hyperparameters are chosen. So for example, how many hidden layers you have in your neural network or how many nodes you have. This is then used in the next step for the actual ML model training, where you apply compute resources from GPUs or CPUs to actually train the model, and in the next step you basically evaluate the model to measure its accuracy. If you're then happy with your model, you could either do another cycle, get new data, or you could also go to the next step, to the inference, where basically deploy your ML model and then continuously monitor it to measure its performance and loop this back into your training phase in the next step. So how does this interplay with cryptoeconomic systems? So cryptoeconomic systems typically are targeted for resource allocation. And in this ML workflow, we also have resources allocated, which are really important to get this ML workflow to life. So to succeed in the ML workflow, we typically have 4 resources. First, we have compute, which is like the most prominent, where we have the, for example, shortage of NVIDIA GPUs. And compute is really important for the ML model training and then also later in the inference phase. Then another really important resource is training data, where you need a lot of data and you need to prepare the data that you can engineer the features and that you can loop it in your ML model training. And then the third type of machine learning resource we have is the expertise, which we need basically to design this whole ML workflow, and also, for example, for the targeted model selection or hyperparameter optimization. And then, last but not least, we have like the outcome of everything, which is like one of the most important resources. It's the actual ML model, where we also have like a huge concentration of big players, for example, OpenAI or Anthropic. So now, since who controls resources controls the ML workflow, it's really important to know where are we getting those resources from. And here I brought a small chart which basically maps the imported and owned ML resources for the country. So as you see, for the United States, they own the compute, they own the data, and they own the expertise. They basically import really nothing. The same is for China. They import a bit more, but they are still owning a lot of their ML resources. And if you look now for France, Germany, or the UK, you see that we are massively importing the ML resources and own basically nothing. And this basically gets a geopolitical challenge, which we have to attack now, and where cryptoeconomic systems can help us. Because the thing is that we are leaning towards centralization when we stick with this model. So what happens if we stick with this model? We basically use the ML-based services from all the big providers, from OpenAI on Trophic. We generate data through our inferences, or when we upload our heartbeats to Apple, and all the data we share online. They are basically used for the company. They enhance their ML resources, they train new models, and they are basically then dictating us what we can do. This also gets cascaded, where we basically have companies where we supply the ML resources to, and they basically use the big hyperscalers, let it be Google, Amazon, or Meta, and they basically then dominate everything that they have. And here, since we have this dominance of the hyperscalers, then they basically can dictate the pricing that we have to pay for our ChatGPT subscription. They can censor information which they want to show us. And what we are losing is basically that we are losing our digital sovereignty. But now I want to give you a new thought where we basically think of how we could build like a collective hyperscaler where we own the machine learning resources and where we participate in the growth and in the improvement of the ML models. So basically we are looking for an open and distributed infrastructure where individuals and companies can really own their ML resources and provide their own ML resources. So for example, if I go back to my example with my heartbeats, I could supply my data, but I have full control over my data, and I can decide for which ML model improvements or for which ML model training I'm donating my data, or maybe I could also get rewards for donating my data. And then it's also that if you have a more decentralized provisioning mode for ML, you can also negotiate custom terms and policies. For example, then OpenAI could not change the usage of ChatGPT on a daily basis. And here, combining with cryptoeconomic systems, the goal is to have an incentivized participation for all machine learning resource providers and consumers that are financially awarded then. Here, this is when cryptoeconomic systems come in play. So basically, to give you a bit research-based definition of cryptoeconomic systems, they basically enable users to manage the ownership of assets by representing assets as digital tokens and leveraging cryptographic principles. And we have the big ones you already know: Bitcoin, Ethereum, and USDC. What they offer is that they offer decentralization, that there's no single point of failure and nobody who centrally controls everything. They offer tokenization, so basically tokenize ML resources that you can trade with them and exchange them. Cryptoeconomic systems can basically put payment rails for the machine learning systems, and they can also offer incentivation to basically steer all users in the machine learning system towards a collective goal. Here we also have some projects which already implemented cryptoeconomic systems for machine learning resource provisioning. Let it be ASI, which is like Ocean and Fetch. They implemented a system, they tokenized, for example, training data, and others also did it. For example, Akash Network, they are tokenizing compute power, and BitTensor, who are have a lot of different subnets where they do ML model inference, compute, or training data. But the thing now is that they are all using different approaches for tokenizing machine learning resources. They tokenize different machine learning resources, and especially when it comes to training data, this often leads to really fractionalized markets where you have machine learning resources that diverge in small parts. For example, training data, we can have a huge amount of data sets, and if each data set needs to be tokenized, we have fractionalized markets, and you still need to provide efficient price discovery and efficient liquidity for those. So this is basically what I want to present you now, a framework that helps to design cryptoeconomic systems for machine learning resource provisioning. Since this project has basically an academic background, I also want to give you a short overview of the research method that was applied. So basically first the ML resources were applied, which I already presented you shortly. And in the next step, a literature search was conducted to identify common tokenization schemes. So basically token designs, which you could then apply to the ML resources in the next step. and everything was iteratively validated with expert interview with experts in the domain and also founders of those cryptoeconomic systems for ML. And what comes out is basically a tokenization scheme that can be used, and it's also an outline of how you could issue those tokens for machine learning resources, and then also how you could design appropriate incentives. So, to give you an overview of the framework, what we're basically having is that we have the 4 machine learning resources. It's compute, training data, machine learning algorithms, and the ML model. And then we have 4 principal types of tokens. So when we go for compute, it also has its own characteristics. For example, it has high variable cost. It's like a physical and tangible asset, so you cannot really replicate it. It's no digital good, and it's typically fungible. So as long as I'm operating on an H100 GPU from NVIDIA, it doesn't matter on which one I'm operating. Then we have training data. It's highly non-fungible. We have a broad variety of different training data sets. And here it's also duplicatable at 0 cost because it's like a digital, non-tangible asset. The same applies for ML algorithms. They are duplicatable and non-fungible because they are all different algorithms. And the same also applies for ML models. Then we identified 4 principal token types. They are like 2 access tokens. First, the permanent access token, which gives you permanent access to the machine learning resource. And this is basically spendable, that you can log it to your identity, and then you have indefinite access to that machine learning resource. Then we also have the temporary access tokens, which are then also spendable and give you access for a fixed time to access the ML resource. Then we have the curation tokens, which are more like comparable to stocks, because you can then curate on machine learning resources and basically signal the quality and value. So basically, when you have fractionalized markets, it allows you to assess which ML resources or which training data, for example, is of high quality and will also improve my ML model the most. And then last but not least, we have payment tokens that are like a universal means of payment, which can be used to pay for any kind of machine learning resource. Maybe an interesting part here, what's important for differentiating the tokens. So we have permanent access and temporary access tokens, and those tokens are basically investment vehicles where you can invest, and you have basically prepaid consumption of an ML resource. So I could buy a temporary access token for compute now and use that token later. So I already log in that I have bought the compute. While the payment token is different, it's more like post-paid because I consume the compute power and then pay for it with my payment token. What we then did is that we mapped those tokens to the machine learning resources, how they can be implemented. Maybe to give you like the most prominent ones, it's basically that permanent access tokens cannot be used to tokenize compute resources because the compute resources have high variable costs and therefore would not be able to be represented by a permanent access token. The same also applies for curation token. You can really use it to signal the quality of training data, ML algorithms and ML models, but it's really difficult to really signal the quality of compute. So this is basically the framework and the mapping we built for the representing ML resources with different tokens. And next I want to present you one practical example, how it could look like. So for example, we have the Akash network, which basically enables market for compute resources and allowing consumers to lease like those distributed CPUs and GPUs for the ML model training and ML model inference. How they do it is that they have on the Akash, so we have the compute provider who then implements those steps of the ML workflow, so ML model evaluation, hyperparameter optimization, model training, and model deployment. To pay the compute provider for providing the ML resource, Akash implements its AKT token, which is like a universal payment token. They issued it with a fixed supply. And if you, as a consumer, want to use the compute resource, you have to use your USDC and buy the AKT token from, for example, a centralized exchange. Because here, as I said, the token issuance is also really important. And since this is a universal payment token, it has a pretty big market. So centralized exchanges are pretty suitable here, and you can acquire your token there. Also, the centralized exchanges allow for a really efficient and flexible price discovery for the price of the AKT token. The compute provider then basically, in Akash there are multiple compute providers, and they have like a sealed bidding mechanism where the compute providers basically offer you a rate for which you can rent one H100 for 1 hour, for example. And then they bid, and you can choose the cheapest offer or the best offer for you based on the price, the localization, or like latency times. And then you spend your AKT token to access the compute resource and can then use it on your consumer side. Yeah, so what's a big advantage here? So it massively increases price efficiency because you have really competition between the compute providers, and since you have a bidding mechanism, they also tend to lower the price to get to give you the best offer and that you take it. And then the second point is that Akash also massively increases the transparency in pricing, since you can always see which prices others are getting and what's like the best price that those compute providers can offer you. Yes, so I would also have the same for Ocean, a bit more complex, where they have like training data, and they basically give the training data provider its own freedom to decide whether he wants to use a temporary access or a permanent access token, and then he can also completely design how it will be issued, so they can use bonding curves to basically model the supply dynamics of their temporary and permanent access token. And here Ocean, for example, also has its payment token, which is like an intermediary for buying the permanent and temporary access tokens, and then gets a new dynamic since you have those Ocean tokens, which you somehow need to hold, but you can already invest in temporary access and permanent access tokens early on. So this is basically a short overview of what cryptoeconomic systems for machine learning provisioning could look like. But what are they useful for now? So I want to give you a short overview of what comes next for machine learning and cryptoeconomic systems. So with this framework, we basically enable decentralized markets for ML resources. That means we can tokenize compute power, training data, and ML models for seamless exchange and more efficient exchange. This can also lower the entry barrier for machine learning resource, for example, training data providers, that I can supply my health data, for example, to train an ML model for recognizing heart strokes, and I will be rewarded. It's not that I'm spending my data like for free to Apple and they extract information from it. And then we can also have like incentivization that could also drive that widespread data and information sharing and allow the monetization of those machine learning resources. When we then go to next step, we could also, if we have this foundation for having the machine learning resources available in the cryptoeconomic system, we can also build new applications for machine learning and AI. For example, if we then access ML models, we could also add like verifiable ML model inference that basically then forms a trust anchor, and you can always validate that the ML model was actually executed, and especially when you go towards fully autonomous agents which are acting on your behalf, you want to have a proof that this ML model was actually executed and that this decision was made by your agent through the ML model inference. And if you have this, you basically can continue and grow to agent economies which leverage those verifiable and decentralized machine learning models. They will then also use the payment tokens or stable coins for efficient payments in those agent economies. And then those agents will also become like a type of wrapped ML resource, and they will also become investable assets, because then you can also like signal the quality of agents by buying its curation token and then also participate in the success of this new ML resource. That's my presentation. Thank you very much for your attention, and I'm really open for your questions now.